Welcome back friends, our YouTube channel TechTide Digital Lifestyle for our Induction Motor Complete course. Today in Day 5 we are going to study one of the most important performance characteristics of an induction motor, which is the torque equation and the torque slip characteristic. These topics are extremely important for understanding how the motor behaves at starting, at normal running condition, and under overload, and they are also very commonly asked in ETO and COC examinations, so please pay special attention to the formulas, the conditions for maximum torque, and the shape of the torque speed curve before starting this video. Like and subscribe my YouTube channel. Let us start by understanding what torque actually means in an induction motor. Torque is the rotational force acting on the rotor that causes the shaft to rotate and drive a mechanical load such as a pump, fan, or conveyor belt. The magnitude of torque depends mainly on two factors: the rotor current and the air gap flux produced by the stator. When rotor current is large and the air gap flux is strong, the developed torque is high, and when either of these reduces, torque also reduces. Because rotor current itself depends on slip, torque is closely related to slip, which is the difference between synchronous speed and rotor speed divided by synchronous speed. From electromagnetic theory, we know that force on a current-carrying conductor in a magnetic field is proportional to the product of current and flux density, and since torque is produced by this force acting at a radius, we can say that torque is proportional to rotor current multiplied by air gap flux, which is written in simple form as T proportional to I2 times phi. This is the basic physical meaning behind the torque production in an induction motor. Now let us move to the practical torque equation used for analysis. When we derive the expression using the equivalent circuit of an induction motor, we obtain a relation in which torque is proportional to slip multiplied by the square of the rotor-induced EMF and rotor resistance, divided by the sum of the square of rotor resistance divided by slip and the square of rotor reactance. Although this expression may look complicated at first, it is very important because it clearly shows how torque changes with slip and how rotor parameters affect the performance of the motor. Next, let us discuss starting torque. At starting condition the rotor is stationary, so rotor speed is 0 and slip is equal to 1. Under this condition, rotor-induced EMF and rotor current are maximum, and therefore the starting torque can be quite high. The value of starting torque depends strongly on the rotor resistance, which is why in slip-ring induction motors external resistance is added in the rotor circuit during starting to increase starting torque and limit starting current. Another important concept is maximum torque, which is also called pull-out torque or breakdown torque. This is the highest torque that the motor can develop without stalling. From the torque equation, we find that maximum torque occurs when the effective rotor resistance divided by slip is equal to the rotor reactance. A very interesting and useful result is that the value of maximum torque is independent of rotor resistance. However, the slip at which maximum torque occurs does depend on rotor resistance. This point is very frequently asked in examinations, so remember both the condition and this conclusion clearly. Now let us look at the torque slip or torque speed characteristic curve. If we plot torque on the vertical axis and slip or speed on the horizontal axis, we obtain a curve that starts from zero torque at synchronous speed where slip is 0, rises to a maximum value at a certain slip called Sm, and then decreases again as slip further increases toward 1. At starting, when slip is equal to 1, torque has a certain value known as starting torque. The region between zero slip and the point of maximum torque is called the stable operating region, because in this region an increase in load causes a small increase in slip and the motor automatically develops more torque to balance the load. We can divide the torque-slip curve into different regions of operation. At starting, slip is high and speed is low. In the normal running region, slip is small and speed is close to synchronous speed, and this is where most motors operate in practice. At the pull-out or breakdown point, torque is maximum and the motor is just on the verge of stalling. If the load torque exceeds this maximum torque, the motor will slow down rapidly and may stop. There is also a generating mode when the rotor is driven above synchronous speed by an external prime mover, causing slip to become negative and power to be fed back to the supply. From ETO and COC exam point of view, you should be able to derive or at least explain the torque equation, state the condition for maximum torque, draw a neat and labeled torque slip characteristic curve, and explain how starting torque depends on rotor resistance. These are classic questions in electrical machines and are almost guaranteed to appear in some form in competitive and certification examinations. To summarize today's DAY5 lecture, we have studied the meaning of torque in an induction motor, the basic and practical torque equations, the concept of starting torque, the condition and nature of maximum torque, the shape of the torque slip characteristic, and the different regions of operation along this curve. In the next lecture, we will study starting methods of induction motors and why different starting techniques are used in practice. So please like the video, subscribe to the channel TechTide Digital Lifestyle, and continue learning with us in the next part. Thank you.